Alrighty, back to this. I'm on example 5, page 206. A was a straight line. Straight lines are always functions. Their domains are always negative infinity to positive infinity, and the range the same, always. Oops, that's supposed to be parentheses. And again, if you know what the graph looks like, it's a straight line. You should be able to tell it's a function using the vertical line test. And you can also tell this goes forever and ever this way and this way, range and domain. Okay, B is a square root. Square root graphs look the same. They're always a half of a U. They start different places. You can set this greater than or equal to 0 to see where your graph's going to start. The x's start at 1/2 and go forever and ever, so that's your domain. 1/2 to positive infinity. And then your range, you can tell from this graph what your range is going to be. Your range is your y values. They start at 0, that's the lowest point, and they keep going up and up and up forever and ever. So that's your range. Okay, C is a C down here, John, is a parabola. But the y is squared, it's going to turn this way, your parabola. Can you tell from the graph whether it's a function? Not a function, because it fails the vertical line test. All right, what about the domain? It does have a definite starting point on the x values. Starts at 0, and then it goes forever and ever to the right, so it never ends. There's not an ending point. And then the range definitely keeps going forever and ever up and down. So the range would be negative infinity to positive infinity. And then on D, example D, when you have an inequality, it is not going to be a function more than likely. Not a function. And the domain and range, I don't know if it wants that or not. Domain and range, it says, can be anything. So negative infinity to infinity for the domain and the range. All right, and then on E. If you'll notice on E, you have an X in the bottom. Okay, if you have an X in the bottom, the graph is going to look like this. There is a value X cannot equal. X cannot equal 1, positive 1. So your graph is not going to ever cross positive 1 here. So what's your domain? Your domain is anything up to positive 1, not including positive 1. And your range here is also restricted. Your range can be anything but 0. 0. Y could never equal 0. Your range is your y values. It can never equal 0. The only way it could equal 0 if there was a 0 on top, and there's a 5 on top, so it's never going to be 0. Alrighty, let's go back to page 208. Tell me when it gets close to 10 minutes. Function notation. If you see something like this, come up here. Y equal x plus 5. Y is a function of x. Y depends on x. The value of y depends on what x is. If x is 4, y is 9. If x is 0, y is 5. The value of y depends on x. Okay, here's another way to write it. Y is a function of x. These are interchangeable. So if you have y equal 9x minus 5, that means the same as f at x is 9x minus 5. F at x, the function values at x, is 9x minus 5. These mean the same thing. What if you're given this? You want to know f at 2. You can say f of 2 or f at 2. Basically, what you want to know is what is the y value when x is 2. When x is 2, you just plug it in right here. Plug in a 2 for x. And what do you get? Oops, it's minus 5. So you get 18 minus 5, and that is 13. So f at 2, the y value when x is 2 is 13. The x value is 2, the y value is now 13. In your brain, you got to get this straight. This is the same as y values. These are function values. They're the same as y values. Okay, 208, example 6. We have f at x. Your function is defined as negative x squared plus 5x minus 3. Another way to write that is y equals negative x squared plus 5x minus 3. And A wants you to find the value of the function when x is equal to 2. F at 2, f of 2. Both those mean the same thing. What does it mean for us to do? Notice where the 2 took the place of x. So that's my x value. I'm going to plug that in for x. Whatever's here goes in the place of x. And then just work it out. That's negative 4 plus 10 minus 3. 6 minus 3 equals 3. So when x is 2, the y value or the function value is 3. That's your answer. Let's do one more. F at q. This is B. F at q. What in the world does that mean? Well, you're going to plug in q for x. Minus q squared plus 5q minus 3. Example 7. Using function notation. Look down here. You want to find f at 3 on each one of these functions. So the first one is f at x is 3x minus 7. Find f at 3. Again, what does that mean? Plug 3 in for what? For x. F at 3 is 9 minus 7 or 2. All right, look at B part. When x is 3, what's your y value? So find the one that has the x value of 3. So f at 3 is equal to 1. Right there. And look at this one. When x is 3, your domain value is 3. What's your y value? 5. And over here, when f is 3, we have to actually count. When x is 3, what's your y value? What y value corresponds to x is equal to 3? It appears it's about y equal 4. What's that point right there? When x is 3, y is 4. Okay, so that's 4 ways to find f at 3. And page 210, example 8. Assume that y is a function of x. Rewrite each equation using function notation. Then find f at negative 2 and f at a. So first thing we look at is our equation. Okay, we're assuming that's a function. First, rewrite it using function notation. Y is the same thing as f at x. So that's step 1, first thing they wanted us to do, function notation. Then find f at negative 2. What does that mean? Plug that in for x. And just work it out. Negative 2 squared is 4. 4 plus 1 is 5. Okay, and then find f at a. Just plug a in where there was an x. And there's nothing else you can do. Okay, on page 211, this is the last thing. I'm going to try to squeeze it in 20 seconds. A function increases if it goes up from left to right, decreases if it goes down from left to right, constant if it's straight across like this. And that takes care of section 2.3.